to
Oh,
blend
Shimazu
identify
says
pages.
Shimazu company products.
In this case, we have
improve
very particular
X-ray
design
generator.
without twists.
The Siemens made micro focus X-ray generator units now including a newly developed irradiation window. Due to the large proportion of the source X-ray in X-ray output, it offers significantly improved contact frame scanning, low density materials, and easy treatment transmit X-rays. In addition, the irradiation angle has been optimized for the wide field flat panel detector. New automated CT scanning function. The new automated CT scanning function enables scan parameter to be specified easily. Simple select material, the result CT imaging resolution and the context level, and the system automatically optimizes the CT scanning parameter scanning accordingly. HPC Inspector High Performance Computer System version 2. The new HPC High Performance Computer System is around 50 times faster provided version. 3D CT scanning region display function. As the CT stage moves, the constructing CT scan region is the display override the real time of the MPR display. This provides CT scanning imaging, adding CT scanning for the area of interest can be obtained. Unit function. CT scan. Complete region or CR can be used to obtain transmission imaging without discerning in the CTZ direction by acquiring data only along the vertical center line of X-ray detector by moving the CTZ axis vertically. Acquisition model switching function. Long or short scan time can be specified by the combined acquiring model and the explorer time setting. Conversion function. CT imaging data can be converted to the DNCOM format, which is the world standard for the medical imaging. Consequently, the function is essential for the imaging data with the medical imaging analog software. French prevention mechanism. A fingerprint prevention mechanism provides a prevent accident when the cross the cylinder door. Collision sensor. Collision sensor are provided along the X-ray tube with to the step the CT stage in the event of the emergency connection with the sample. The collision sensor window can be opened or closed depending on the magnification rate. Image Pro Analyzer 2D image processing software. The two-dimensional imaging process software enables sophisticated imaging processing. Makes a 3D imaging processor software. This is extended version of VG Studio, extended functional including animation creation, rotation, trading, the viewpoint movement, measurement of range angle, minimum distance, histogram, volume, surface area, void ratio, ROI extension, extraction, imaging, plotting, and multiple 3D imaging arrangement. Polygon Mirror. Polygon Master is polygon editing software which solves various problems of pitch, noise, and article polygon provided by measuring surface object. Application. GFRP glass fiber plastic cross. Lithium recycling battery software mouse. Let's array project versions expansion analysis specification 島津製作マイクロフォーカス島津マイクロフォーカス新 UT 搭載による直感的な操作実現扉を閉めたらすぐに検査を開始初めての方でも簡単に X 線検査が可能です高性能完全な2分以内大型モニター採用教育可能です大型モニター外見画像で1決めステージを全体に撮影しますクイックさで部分レベルをするのが可能になっています、実現しますモニターから視線を外すことで素早い移動が可能です中心移動 X 線画像表示をクリックするとクリックした位置が標準位置に中心になります拡大、ドラッグするとドラッグした表示するように拡大しています Easy Scanning System
My hope is definitely that I can actually use all this time
その
in
X 線、CT の切り替えはメニュータブを選択するだけで可能です
to continue
CT
further this
撮影
work
条件
because
は撮影モード
there's just
撮
too
影
many
角度
unknowns,
撮
so
影視
I'm
野を
just
選
going
択するだけで
to
簡単設定
motivate
ポイン
all
ト
the
する
work
に
that
シ
we've
ー
been
ンで
trying to do
撮
ever
影
since. So this work is basically what's contained in the paper of already a year and a half ago. But well, we've tried many different things from then on. Unfortunately, just yeah, there's more unknowns than actual full understanding. So the main idea is that so in I didn't try this, so I am focusing on
ワイヤー流れ系ウィンディングワイヤーで大きな
ADS3 process 3 cross T4, and I am studying.
プリセット
I will be studying basically classical string solutions and their semi-classical behavior and trying to compare to what integrability tells us that these behaviors should be. And in particular, we were very much interested in circular strings.
高性能ハンディスピードカメラ
in the sector of R process 3,
ファントムク
it's
エ
very
リテ
well
ィ
known what
抜群の機動
semi-classical
率性
behavior is. It was calculated
高速度可能な撮影ができますアプリケーションでハイスピード撮影もっと自由
and
に
basically, well, it's R
作
process
業
3,
効
so
率
they
大幅ア
have
ップ
the normal
簡
shape
単セッ
which
テ
is
ィング
written here. The
コン
charges
パクトバ
can
ッテ
be
リー搭
written
載タッチパネル式モニター
in
イ
terms
メー
of
ジ
the curl, what I call the
Ah,
curly J,
mount
which
lens.
we then take to be very large.
Quantum.
The energy is related to the charges by the Virasoro constraints in the usual way.
カメラですね
The
ハイス
idea
ピ
is
ード
that,
が
okay, with the circular
スローモー
strings, we want to do a semi-classical calculation, and the semi-classical calculation is very much related to what can be found in ADS5 process
ハンディ
5.
カメラまだあります
A lot of the calculations so as with any classical strings, we're
非
talking
接
about
触3次
from
元
the point of view
挙
of
動計測システム
integrability of massive excitations. And in many of the calculations that you can do in the integrability, the
ということで
massive sector seems to be
切り作業に移
happy
り
on
ま
its
しょう
own and doesn't it really interact with the well, the massless excitations don't really
やっぱり
contribute
話しましょうかね
to
今日
you know, if you're trying to do scattering of massive excitations,
3D
the massless
solution
excitations are
machine
not there.
vision
If you do BMN scattering
ポ
also,
ータブ
you
ル
can just
3次元
focus
レ
on
ー
the
ザースキャナ
massive sector, and massless excitations again do not play a role. But what happens in this case is actually if you try to do the semi-classical quantization of certain classical strings, what I will try to motivate is the fact that actually the massless excitations do play a role, even though you'd expect them to still decouple. So, in terms of the worldsheet semi-classical quantization, you calculate modes, set of modes. They have some fermionic modes, some bosonic modes, and for this particular case, you actually have massless modes as well. There are 4 bosonic massless modes associated to T4 and 4 fermionic massless modes. What happens about these the frequencies of these modes is that if you once you sum them, basically they cancel out, and what you're left with the two bosonic modes of S3, which are basically two of the modes that you would have from S5. Two bosonic modes in ADS3, again inherited from ADS5, and four fermionic modes. In the same way as the calculation can be done for ADS3, for ADS5 plus S5, you need to, when you sum these modes, you need to regularize by the typical method of Bison-Sapling. You regularize. Actually, you're interested in the non-analytic terms because we are trying to compare to. We will want to compare to the one loop dressing. But so once you do a regularization, you basically obtain exactly what I've written here, which is what I call delta E string. You have it as an expansion in J, in the charge J, and you can hope to compare it actually to now beta ansatz calculation. Why? Because, well, we are talking about a consistent sector which is related to R cross S3, so it's the SU2 sector of the beta ansatz equations. If you do if you analyze this sector, meaning I've written here the beta ansatz equations, of course this dressing phase now is going to be different. Why? Well, so the dressing phase, I've written it as with the coefficient CRS times the charges. Of course, the classical component is just the AFS, because we're talking about strings in R cross S3, so it's we would expect the AFS. This is the massive sector because, well, it's the SU2 massive sector of the theory. And of course, now here the one loop dressing phase is what would come as a semi-classical contribution, and that one will naturally be different from ADS5 cross S5. These coefficients are known. They're known from, they're being fixed by crossing symmetry, by scattering of magnons, by BMN scattering. So, meaning it's known, they're known, and completely defined. This is the relation. And in particular, because we're doing strings in SU2, we're doing circular strings, we know the resolvent that is associated to the one-cut solution in SU2, which is a circular string. I've written here. Of course, if I expand this one-cut solution in the spectral parameter X, I get the classical charges. And how do I now obtain the semi-classics? Well, what I can do is just do the test that Hernandez-Lopez did at first place in ADS5 cross S5 when they wanted, in fact, to calculate this one loop perturbation to the dressing phase. So if you indeed do that, what I mean by doing this procedure is just so I have the one cut, again, I have the one cut circular string resolvent. I just take the logarithm of the beta ansatz equations. I convert any sums over the roots into integrals. Sorry. So by basically a sum of k of x f of x k plus minus becomes some L integral over the cut dz. So rho is associated to the resolvent by just that. By the usual way. So I basically yeah, take the log of the Betances equations, convert every sum into integrals, and then what I want to do is actually perturb the charges. Appearing in the dressing phase as, I say, Qn is just the classical charges plus 1 over square root of lambda delta Qn. And in particular, this actually for the circular string, why the circular string? The circular string is extremely simple, the result that comes from this calculation, because it's actually, you can write the solution for the perturbed charges, the perturbed energy, in closed form. So it's actually a very simple solution. And basically, you solve for delta E, which is it. It's just the delta Q2, and this has a complete closed form in terms of, so it's sum of RS, CRS1, GR plus S, and then QR plus 1, QS minus QS plus 1, QR. So these are all classical charges. So in terms of the classical charges, so it has a closed form expression, and if you expand this expression, of course, what you get is what I've written there as the delta E one loop. So this was what, again, this was the calculation that was done to, in fact, determine in the ADS5 cross S5 to first determine the CRS ones, because they knew what the classical circular string, the semi-classics were, and they could determine the CRS ones. In this case, meaning we already know from other methods what the CRS ones are, and we can actually determine what delta E1 loop is in terms of those CRS1. The one loop perturbation to the dressing phase, and what happens is that, well, if you subtract these two solutions, of course, you get something that is completely non-zero. So we were baffled by this for a long time, and what in fact we found is that the exact reason why these two results don't match is that the massless sector actually plays, not the massless sector, but the mixed mass sector, so the interaction between massless particles and massive particles actually plays a role in the perturbative energy correction, semi-classical correction. And where does this contribution come from? From wrapping. So what actually happens is, well, our claim is that it does come from wrapping, and what we did was do some, we can say, some somewhat crude calculation, in the sense that it doesn't include or exhaust all contributions to the semi-classical energy, but is definitely of the same order, more of than of the same order, is actually of the same shape as the results, the mismatch that we find. And it comes from the fact that when you have massless virtual particles winding around circle L, and you calculate, field theory calculation of contributions that can be done from Lucier. So here I should write Lucier F terms. What happens is that typically these wrapping contributions would be exponentially suppressed, and exponentially suppressed where the exponential is, the top of the exponential is kind of proportional to the mass. So if you don't have a mass, and I'm going to go back to whether you could actually, whether each one of these contributions actually makes sense on its own, but let's assume that we could just take the massless limit of some of these Lucier F contributions, F-term contributions. So if you actually have a massless particle going around the circle, the it will have some contribution that will be leading, that will be of the same order as the perturbative contributions that we're calculating. So if it was massive particles, massive sector, they would just decouple and be exponentially suppressed. But if you have massless virtual particles going around the circle, these are of the same order and will actually contribute to the final result. So with this, so this is the mismatch, and so where do the Lucia F-term calculations, I've presented here some particular solutions, but I'm going to talk a moment about Lucia. And basically the The Lucia F-term calculation originally came for a relativistic theory of particles of mass, I'm going to write S, and with the dispersion relation, so it's relativistic, so the dispersion relation is naturally and you can
the mass is bounded from below, and the entropy goes like m to 1/2. So it's again well defined, and you can compute the mass, the partition function. Now this is unstable anyway for small m black holes. So this is the way you actually compute this sum. Of course, can be very difficult to compute. There might be a prefactor. I mean, normally at the beginning you just look at the thermodynamical approximation, which means instead of running m, making this sum, because there might be a prefactor and many other details. So a first look is to say, well, for a given beta is what is fixed. For a given beta, I want to look for the value of this exponent such that this is maximum. So the exponent is maximum, and that will give me the main contribution to the partition function. Looking for this, the maximum value of this is the same as looking for the minimum values of that. So this is the effective action. And then you plot. You just say, well, for my given entropy, I have a fixed beta, and then I plot this object as a function of m, and then look for the minimum. So in 3+1 dimension, this is what you get. These are different values of beta, and then you observe this critical value of beta. This is a very interesting critical value in which the minimum here has the same free energy as m equals 0. M equals 0 is, of course, the ADS background. So if you have beta smaller than the critical value, then the minimum, the true minimum of the partition function is this one, and if beta is bigger than critical value, what you would call the black hole solution has a bigger free energy than the ground state. The ground state is this red point. So it's quite clear what happens from here. The solution will tunnel down to the ground state, and if you're here with this value of beta, then the black hole solution has the minimum energy. So this is a partition, the effective energy view of the Hodgkin-Page transition. This is a Hodgkin-Page transition. When you are here, then of course the system will prefer to go back to the background. Now in 2+1 dimensions, the situation is slightly different, but the physics, I would say, is the same. In this case, there are no solutions here. Well, there are this so-called conical solutions, but the conical solutions are not solutions of the free action. They need a source. So if you have just pure gravity, then and this is m, from m equals 0 to infinity there are solutions, and then here there are no solutions, and then at m equal -1, or depending on the various conventions, but at a negative value of m, then you have ADS space. So in this case, this is ADS space, and then from m equals 0 to infinity, there are black holes. And again, you have exactly the same discussion. There's a critical temperature where the minimum of this curve is at the same value of the ground state, but then for smaller values, the black holes will dominate, and for bigger values, the ADS ground state will dominate. So this is again a Hodgkin-Page transition in 2+1 dimensions. Okay, so what we shall do here is to do exactly as I just said. These are very old results, but in the case of high spin black holes. So that means I will work in 2+1 dimensions, which is a theory where you can couple high spin charges in a very easy way, and then consider the same problem. I will have a partition function given by a set of n-1 charges, Q2, Q3, Qn, with their corresponding chemical potentials. Mu2 and Q2, you can think of them as like the first one would be like the temperature and the mass, and then all the other ones are the high spin charges. So mu3 to mu-n are fixed numbers, the chemical potentials, and the entropy will be some function of only the charges. So the idea is to look for the minima of this free energy, and then try to extract the different phases. Yes. You will need to, well, I'm not very, sorry, my hearing is not very good, and
so the question is, when you consider these n charges, do you assume that they form a closed algebra as with respect to Poisson brackets, or just any conserved charges are okay in this construction? Higher spin.
I mean, by this construction, the charges will form a closed algebra.
Yeah, that is the question.
Yes, yes, yes.
Okay, thanks.
Yes, they will do. Okay, so my table of contents will be a quick look at the SL and R Chern-Simons theory and how these extra charges arise. Then looking at some comments about the spectrum of solutions for these theories, and then looking at the phases, and then what we'll see is that, so first we'll have to find the solutions, an interesting set of solutions. Then we will look at the partition function for this problem, and then look at the different phases for given values of the chemical potentials. And then we will see first that there are Hodgkin-Page transitions, so there are values of the chemical potentials where the solution or the system will prefer to be on the ground state and not on the black hole solutions. So that will be a situation where the Hodgkin-Page will act with the Hodgkin-Page transitions, but also it's a rich set of transitions, because there could be transition between black holes. So that means that I have some given values of the chemical potentials, and then I have a black hole, and I move these chemical potentials smoothly, very slowly, and if I cross a given boundary, I cross it, then this black hole will go into another black hole with completely different properties. So that we will call a transition between black holes. This is something you don't see in Schwarzschild ADS, for example. So this is very similar. I mean, the mathematics is exactly the same as the Van der Waals-like fluid. Of course, the formulas are very different, but the pictures at the end are exactly the same. So it's like going from the gas phase into liquid phase. It's a very similar situation. And also there's a secondary transition where you have this, you will see this critical line connecting different black holes, and then you move in the other direction, and eventually this critical line disappears, and there's a critical point. So this is basically what I will be talking about. As you see, this is very old stuff in a way. This conference is recent development in ADS3 CFT2, but this is actually a very old application of statistical mechanics. So this is my only slide on Chern-Simons, SLN, Chern-Simons, and the gravitational interpretation. So the idea is that you start with two SLNR Chern-Simons fields. You need two of them. I will call them A and B. In the literature, you will see one is called A and the other one is A bar, and then when you have complex field, there's a bar and a bar, and then it becomes very complicated in notation. So I prefer A and B. It's a bit simpler. So I have two Chern-Simons fields, A and B. They live on the SLNR algebra, and the equation of motion for both of them are the same, just the Chern-Simons equation. And the trick is that if you define a field that I will call E at the difference of both, and then W as the sum, of course this is an invertible transformation, and then from out of E I can build this trace of EE, trace of EEE, E4E, etc. up to NE. If I have chosen already my N, so this will stop at N. If you compute the next one, it will give you 0. So that means that in particular if you have N equals 2, then the only one you can define is this one. But if you have a bigger N, then you can define all these objects. They're all symmetric. And the beautiful statement is that if A and B satisfy these two equations, then all of these will satisfy frontal higher spin field equations when linearized. This is in 2 + 1 dimensions on ADS background. So this has been, well, it's a development. There's a lot of, I was not very careful citing that. I should have included here the literature. There's a lot of literature in this problem. So from my point of view, what I will do is that this gives me a theory of N-1 higher spin fields interacting. This is the interesting point. This is interacting, and the equation of motions are extremely simple. This is just two Chern-Simons field equations. So this theory, first of all, has an asymptotic Wn conformal algebra. There's some references here. Good. This was done simultaneously by two groups. This is, you can analyze the asymptotic algebra, and then you discover this Wn algebra. There are solutions carrying all charges, so there are charges associated to this algebra, and then you can build explicitly solutions carrying these charges. It's not quite clear what black holes should look like, so that means that it's not very clear to define the global structure of black hole. Of course, you can find something that will look like a Schwarzschild black hole, but it's very tricky. It's extremely tricky. A black hole is not really something that looks like Schwarzschild. The global definition of black hole is a far more complicated object. And in the case of these higher spin charges, higher spin theories, the main problem really is the symmetries involved. Now you don't have only diffeomorphism, but you have a much bigger group. And you want to define the horizon, for example, in a way which is invariant under, not only under diffeomorphism, but under a much bigger group. And that's something, to my understanding, maybe somebody have mentioned something before, but this is not well understood. Funnily enough, even if you don't understand very well the global properties of black hole, you can compute the entropy, for example, at least for something that you can say, well, this will be my black hole. At least there's a partition function I can compute, and there's an entropy and a temperature well defined. Okay, so let me consider two classes of solutions. This is the simplest you can do. First of all, the problem is understanding a gauge field with 0 curvature. So this is the problem. This is a diffeomorphism invariant theory. It has a 0 Hamiltonian. The time evolution is trivial. The time evolution should not